This experiment is Compton scattering and the determination of the transmission coefficient of aluminium. In the experiment, X-ray unit has a GM counter which can only detect the number of photons incidenting on it. The energy of the photons cannot be measured. Hence, we are measuring the transmission coefficient of X-ray photons through aluminium absorber as a function of wavelength. We done previous experiment in the same apparatus. You already know the setup of the experiment. Now I am going to show the component we are using in this experiment. Aperture is 2 mm diameter and the lithium fluoride crystal. Aluminium absorber, the thickness is 0.08 mm. We have already fixed the aperture here. Mount the lithium fluoride crystal in the holder of the goniometer. Before starting the experiment, we have to calibrate the setup. Start calibration. Go to menu. Select goniometer. Enter. Now we get the auto calibration. Press start here. Auto calibration process is started. See the calibration scanning range from 10 degree to 55 degree. You will get the continuous spectrum called as a Bremsstrahlung. The plot now appearing is K alpha and K beta lines. This plot is called characteristics of copper anode tube. You can see here. Now auto calibration is done. Start the experiment by placing 2 mm aperture here. Insert the lithium fluoride crystal in goniometer. Then close the door. Connect the X-ray unit is interfaced to the PC through USB cable. Measure software will be displayed on the screen. Go to goniometer. Select the parameters. Mode is 1:2 coupling mode. Crystal is lithium fluoride crystal. Starting angle is 7.5. Stopping angle is 9.5. Crystal increment is 0.1 and gate time is 100 seconds. Press OK. Start the measurement in the measure software. Determine the pulse rate of the X-ray scattered by the lithium fluoride crystal between the glancing angle 7.5 to 9.5. After the measurement, the following windows appear. Select, send all the data to measure. Go to measurement, data table, 7.5 to 9.5 readings are appeared. Export data. The measured values will now be transferred directly to the measure software. File name and save. In the earlier experiment, we did not use the aluminum absorber. Now I am using the aluminum absorber positioned in front of the aperture using the plate holder mounting on the optical bench to measure the pulse rate. Then close the door. As you have seen in the introduction video, we have to use the aluminum absorber to find the transmission coefficient. The experimental setup is similar to the previous one. Open the measure software. Select the parameters. Go to goniometer. Parameters are given in the write-up. And then configuration of the experiment is done. Start the measurement. Transmission coefficient as a function of wavelength. First, we are finding out the transmission coefficient of incident and scattered photon. From that, determining their wavelength. Select Send all data to measure. Next, go to measurement. You can see the data from crystal angle 7.5 to 9.5 and intensity readings. Export the data and save to file. To find the transmission of an aluminum absorber as a function of Bragg's angle and plot it as a function of the wavelength of the radiation. In the tabular column, angle in degree, the angle range we have set in the measure software 7.5 to 9.5. Intensity without absorber, that is I0, intensity with the absorber I, and find out the transmission coefficient I by I0, and wavelength using the formula 2d sine theta is equal to n lambda in picometer. Plot the graph. The relationship between the wavelength lambda of X-ray photon produced by the copper tube and the transmission coefficient of aluminum needs to be found out from the table. Transmission coefficient versus wavelength, it should be linear fit. Next part of the experiment is determining the Compton scattering with the component acrylic glass scatterer, aperture 5 mm diameter, and the aluminum absorber. Insert aperture with a diameter of 5 mm into the outlet of the X-ray beam. Remove the lithium fluoride crystal and mount the acrylic glass slab in the goniometer and then close the door. Using the measure software, go to goniometer. Mode is fixed crystal angle. Select last option. This is nothing but no crystal. Detector starting angle is 40 degree. Stopping angle is 120 degree. increment is 10 degree, integration time is 100 seconds. These configurations are given in the write-up. Measure the intensity of the radiation that is scattered at the angle of 40 degree to 120 degree on an acrylic glass slab without an absorber, and determining the Compton wavelength of the electron based on the transmission curve. Select the measurement, go to data table. You can see the reading from 40 degree to 120 degree. The measured value will now be transferred directly to the measure software. In the second part of the Compton scattering experiment, we have to place the aluminum absorber in front of the aperture using the plate holder, mounting on the optical bench. Then close the door. Measure software is already open. Then the parameters all are same. Start the measurement in the measure software. Measure the pulse rate with the acrylic glass slab and with the aluminum absorber. From this, the wavelength of the incident X-ray photon can be determined. Then send the data to the measure. You get the readings from 40 degree to 120 degree. You are repeating the same procedure to store the data. Next, place the aluminum absorber in front of the GM counter tube. And then close the door. Parameters are all same in the experiment. Measure the pulse rate with the acrylic glass slab and with the aluminum absorber in front of the GM counter, and from this the wavelength of the scattered X-ray photon can be determined for the particular angle. Then send all the data to measure. You are repeating the same procedure to save the data. Determining the Compton wavelength angle in degree 40 degree to 120 degree, intensity without absorber N3 as given in the write-up, intensity with the absorber N4, intensity with absorber in front of the scatterer is N5, transmission coefficient of incident and the scatterer you have to find out, wavelength lambda and lambda dash using the formula 2d sin theta is equal to n lambda. Plot the graph. Wavelength at different angle were calculated to check the relation using the formula. It was verified by the plotting the graph between lambda dash minus lambda and 1 minus cos theta, which is linear. Then Compton wavelength was calculated from the slope of the graph between lambda dash minus lambda and 1 minus cos theta, which give an error of theoretical value. You have to find out the experimental value and compare with the theoretical value.